Okay, so let's talk about our next substitution reaction, specifically the SN1 reaction. So again, we're going to be doing a substitution reaction. So let's look at an example here. I'll start with an alkyl halide. Here I'm going to be adding a nucleophile, and what you'll notice in the SN1 reaction is we're generally using weak nucleophiles or weaker nucleophiles. Okay, and a lot of times our nucleophile also acts as our solvent, so you're not going to see an extra solvent in here, so we could use water or methanol or ethanol. And in this reaction, we'll do a substitution, so our leaving group, our chlorine, will be replaced with our nucleophile. In this case, water will form an alcohol in this product. All right. So let's look at the mechanism on how this works, right? So while it is a substitution reaction, there is a difference between the SN2 and the SN1. They're both substitution reactions, so your nucleophile substitutes your leaving group, your alkyl halide, but the mechanism on how this works is very different, all right? So it turns out with the SN1 reaction, the carbon-chlorine bond is first going to break. So we are going to eliminate out the chlorine, or alkyl halide, leaving us with a carbocation. Okay, so that carbon-chlorine bond will first break to give you a carbocation. All right, that is the rate determining step, RDS, the rate determining step of the reaction. And then what can happen, right, is our nucleophile can now attack that carbocation. Forming a new bond from the lone pair on the O to the carbon. That O is still connected to two H's. It now only has one lone pair because the second lone pair formed that bond, and therefore that oxygen has a positive charge. All right, so to finish the mechanism off, we just need to get rid of an H and the positive charge. We need to remove a proton, and we can use another equivalent of water to do that. Our water can come in, steal that H. These two electrons can form the lone pair on that O, right? So that O now has two bonds and two lone pairs and is neutral. So this is the mechanism for the SN1 reaction. So let's take a few notes about the SN1 reaction. Okay, the first thing we talked about is that our nucleophile is generally weak. Right? A lot of times our nucleophile is simply our solvent. Second thing we should notice is that this is a multi-step reaction. Right? This can generally be 2 to 3 steps as compared to the SN2, which is only one step. Okay? Next, I kind of want to tell you is that this reaction is not super useful. Okay, so we generally learn the SN1 reaction to compare it with the SN2, but the SN2 reaction works quite well. You get really good yields. That's not the case here. You don't get great yields. Don't get great yields. Okay, so I want to talk about why that is, right? So in our first step, our rate determining step here, right, our carbon-chlorine bond breaks and we form a high-energy carbocation. So while we definitely can take, let's change our color here, while we can take a path to the right to do the SN2 reaction, there is another path that we can take, okay? So it's possible for us to take a different path, all right? And that different path here is a reaction we've already seen. We can end up doing really an E1 reaction, right? So it's possible for your water molecule to, instead of attacking that carbocation, to now abstract a hydrogen and form our double bond, right? So we've already learned about the E1 reaction, and this is a side product that can and will form, all right? So what you'll see here is that there's really two pathways, right? We have our kind of blue pathway to get the SN1 product, but we can also kind of do an E1 product, or E1 pathway to get our E1 product, all right? So there's two different ways we can go, which means you're not going to get just one product. You're going to get a mixture of products, which means this isn't a great reaction, all right? And the key here is in our rate determining step, right? Whether you go the SN1 route or the E1 route, that's happening after your rate determining step. So the rate of the reaction is determined by this first step here, but then our choice happens after that, right? So what that means is when we change temperature or we change solvent or other factors, those really impact the rate determining step. And because the SN1 pathway and the E1 pathway, that is splitting after the rate determining step, we don't have much control on which way you go. So you normally get a mixture of both products, right? Which means if you're getting multiple products, that's not a great reaction. So it's not super useful, all right? So you'll see we'll learn about the reaction, we need to know it, but we're not going to be using it in a lot of syntheses to make products because it's not as useful, all right? But we still want to learn the reaction so we can compare and contrast, right? And it's important to know when we talk about reactions, we can favor an SN2 over an SN1, right? But you're still going to get a mixture of these products. They're going to be reacting at the same time, all right? But let's kind of continue with our lesson, right? I want to show you another example here. So let's look at something like this. So here I'm going to add some stereochemistry. So that is indeed a stereocenter. What happens if we run the reaction here? So if we take a weak nucleophile and our solvent like methanol, we are again going to be doing a substitution reaction, right? But what happens here now is, as opposed to the SN2, where you have inversion of stereochemistry, if you happen to have a stereocenter, we actually have a loss of stereochemistry. So let's put that up here. We have a loss of stereochemistry at the electrophilic carbon. And why is that, right? So if we think about our mechanism here, our first step is our carbon-bromine bond breaks. We eliminate that out. And what happens to our stereocenter at that point, right? I've now formed a tertiary carbocation. All right, I've formed a tertiary carbocation. Tertiary carbocations are achiral, and that's the key here. This tertiary carbocation is no longer a stereocenter, right? That molecule or that carbon is sp2 hybridized. It's no longer a stereocenter. Okay, so we have an empty p orbital here. So in our second step, when our methanol attacks, we can attack from the top side, right? Or you can attack from the bottom side. We don't have, in inversion of stereochemistry, we don't have backside attack. You attack from either side, right? So when our nucleophile attacks, right, we can equally attack from the top or the bottom, right? Which means we no longer have a dash or a wedge. We no longer have a dash or a wedge. Okay, so while this is a stereocenter, we've lost the identity of it, right? Here, we had our bromine as being back, right? So we drew dashes and wedges. Now, there are no more dashes and wedges, so when our nucleophile attacks, these have to be straight lines, right? They have to be straight lines. That means we have a racemic mixture of the two enantiomers. We have a racemic mixture, right? So if we finish the mechanism here, deprotonate, if I just take, again, methanol, that lone pair can deprotonate our hydrogen. That hydrogen-oxygen bond breaks to form a lone pair on the O. The O now has two lone pairs. That's the mechanism. We see that we have a loss of stereochemistry. So these bonds here have to be lines, right? And that means we have a racemic mixture of the two enantiomers, all right? And that really brings us to our next point when we're looking at the mechanism, right? We know that this first step is our rate determining step, and we're forming a tertiary carbocation, right? Why did I start with a tertiary alkyl halide here? That formed a tertiary carbocation. And what do we remember about carbocation stability? Right? We know a tertiary carbocation is more stable than a secondary, which is more stable than a primary. So this reaction will definitely work with a tertiary alkyl halide because it forms a tertiary carbocation. What about secondary, right? Would that work? Right? So here I have a bromine that's not a stereocenter, right? So if I react this in water, we can do a substitution reaction. We can do an SN1 to form our alcohol here, right? The mechanism would be exactly the same. You would eliminate out the bromine, you would attack with your water molecule, and you would deprotonate. And this reaction definitely will work, right? A secondary alkyl halide will absolutely work. But what if we have a primary, right? What if we have something like this? Will this reaction undergo an SN1 reaction, right? And the answer is no. Why is that, right? Well, remember our carbocation stability. Tertiary is more stable than secondary, more stable than primary. Tertiary will work, secondary will work, but primary won't. Why? A primary carbocation is too high in energy. A primary carbocation is too high in energy. All right, so for the SN1 reaction, it's the opposite of the SN2, right? The SN2 primary works faster than secondary, tertiary doesn't work. In the SN1, tertiary works, secondary works, but primary doesn't. And that's because of the difference in the mechanism, right? Because the mechanism goes through a carbocation intermediate, primary carbocations are too high in energy. So our mechanism goes through a carbocation intermediate. So tertiary reacts and is faster than secondary, which is much faster than primary, so much so that primary will not work. All right, so for the SN1, it'll only work if it's tertiary or secondary. All right. So let's talk about the last aspect of this, about the SN1 reaction, and that is the order of the reaction, right? What does the 1 mean in SN1, right? In our SN1 reaction, what does this 1 mean? The 1 means that this reaction is first order. First order. Okay, so let's take a look at the reaction we did here. Let me recopy that. We took a secondary, we reacted that with water. We got out our alcohol as our product. So what do we know from our rate laws? The rate of the reaction is equal to our rate constant K times just the alkyl halide, right? First order means we only have one reagent, all right? Why is that? When we look at our mechanism, right, in our first step in the mechanism, we have our alkyl halide, the carbon-chlorine bond breaks to give us our tertiary carbocation. The methanol, our nucleophile, is not reacting with our reactant in the rate determining step. In the rate determining step, we break the carbon-bromine bond to form the carbocation. The nucleophile reacts after that. So our rate determining step here, right, there is no nucleophile reacting. It reacts after it, right? We just have to worry about the concentration of our alkyl halide only. Okay, so our rate is determined by the rate is equal to our rate constant K times the concentration of our alkyl halide only. All right? So remember, if I double the amount of my alkyl halide, right, I'm doubling its concentration, the rate would be twice as fast. If I reduce my solvent, reduce my solvent by half, I again have doubled the concentration of this. Remember, that is a concentration, moles per liter. We've doubled the concentration of this if I've changed my solvent. Also happens to be my nucleophile, so my rate is also twice as fast. All right, so the last thing we have to remember here for our little bit of notes, right, is that this is a first order reaction. All right, and again, I just want to kind of highlight all these pieces here. SN1 reaction, our nucleophile will generally be weak. It'll normally be our solvent. It's a multi-step reaction, right? It goes through a carbocation, right? So this reaction will work if it's tertiary or secondary. We have a loss of stereochemistry. So if you happen to have a stereocenter at the electrophilic carbon, that stereochemistry will be gone. This is a first order reaction. And kind of important here, again, the reaction, because it forms multiple products, it's not super useful, right? So we kind of like to talk and learn about the SN1 reaction to compare it with the SN2. But you'll see when I'm synthesizing more complex molecules, this isn't the best choice of a reaction to use.